You know that feeling when you lose your keys? You check the kitchen counter, then your pockets, then the couch, then you go back and check the kitchen counter again, just in case.
The classic human infinite loop. We're terrible at search algorithms when we panic.
We really are. We do it instinctually. But today, we're talking about how you teach a machine to find those keys. And I don't just mean, using a GPS. I mean, how does an AI agent figure out a plan when it has absolutely no idea where the goal even is?
Right. This is search with a capital S. It's really the bedrock of artificial intelligence. Before you can have an AI writing poetry or driving a car, you have this fundamental problem. How do I get from state A to state B without a map?
And to guide us through this maze, we're digging into a lecture on uninformed search algorithms by Dr. Reza Abli from California State University, Channel Islands. So our mission today is to get inside the quote-unquote brain of an AI agent. We're going to see how it navigates a problem space. And I have to warn you, by the end of this, you are never going to look at the game Pac-Man the same way again.
No, you really won't. It turns out Pac-Man is, well, it's a mathematical nightmare.
So let's start at the very beginning. If I want to build a robot to find something, I can't just tell it, go find it. It's too vague. The lecture says we have to model the problem first.
Exactly. You have to define the universe the agent is living in. And Dr. Abdali breaks this down into 4 specific components. If you don't have these 4 things, you don't really have a search problem.
Okay, lay them out for us. What's number 1?
First, you need a state space. This is basically the set of all possible configurations the world can be in.
Configuration sounds a little abstract. Can you make that more concrete?
Sure. Think of a chessboard. Every single possible way the pieces could be arranged on that board. That's your state space.
Which is, that's massive.
In chess, it's astronomical. But for, say, a GPS system, the state space is just all the cities on the map. It's the where can I possibly be of the problem.
Got it. So state space is the map of what's possible. What's next?
Next is the successor function. These are the rules of the road. It defines the actions available. So if you're in a city, where can you go from here? And crucially, what's the cost of that action?
So it's not just I can go north, it's going north cost me 10 miles.
Precisely. It connects actions to consequences.
Mm.
Then the third one is simple, the start state. Where are we right now?
The last one.
The goal test. How do we know we've won?
That seems obvious, right? The goal is I am in Bucharest.
Well, it seems obvious to us, but the machine needs a specific logical test. Is my current state the target state? Yes or no? If yes, stop. If no, keep going.
There's a really important nuance in the slides here. We think the solution is the destination, like getting to Hawaii. But in computer science, that's not it.
No, that's just the goal state. The solution is the sequence of actions, the plan that gets you from your desk to that beach. The AI is producing the path, not just the postcard at the end.
Let's use the example from the lecture to make this solid. We're in Romania.
The classic AI textbook example.
We're in a city called Arad. Our goal is to get to Bucharest. We have a map, but we don't know the best route.
Okay, so let's model it with our 4 parts. Start state is Arad. Goal test is, am I in Bucharest? The state space is all the cities on the map. And the successor function. That's the roads leading out of Arad to Sibiu, Timisoara, and Zirin.
And the cost is just the distance. So our agent is in Arad. It looks at its options. It sees 3 roads. And since this is uninformed search, it has no clue which road is better, does it?
None at all. That's the key. It doesn't have a little voice saying, hey, Sibiu is generally in the right direction. It just knows Sibiu is a valid move. It's flying blind.
This all seems pretty manageable for cities on a map. But the lecture then pivots to Pac-Man. And this is where it gets crazy. And we have to talk about the world state versus the search state.
Yes, this is a concept that trips up a lot of people. The world state is, well, it's everything, reality. In Pac-Man, that's Pac-Man's location, the location of all 4 ghosts, their direction, their speed, the status of every single dot. Everything.
The entire screenshot of the game at that exact moment.
Right. And if you try to plan using all of that data, your computer will just melt. So the search state is an abstraction. It's a simplified version that only keeps the details we actually need to solve the problem.
Okay, give me an example. Case study 1 from the slides. Pac-Man just needs to get from point A to point B.
In that case, do we care about the dots?
Nope, not at all.
Do we care about the ghosts? For this specific pathing problem, let's say no, we just want a route. So the search state is just Pac-Man's X, Y coordinate.
That's it.
That's it. And the board is small, maybe 120 possible positions. A computer can solve that in a microsecond.
Okay, easy enough. But then he drops the hammer. Case study 2. The eat-all docs problem.
And this is where the complexity just explodes, because now the goal isn't get to coordinate X, it's eat every single pellet.
So why does that change things so much? Can't the state still just be where Pac-Man is?
No, because being at position 2, 4 with all the dots still on the board is a totally different reality than being at 2, 4 with only one dot left. The state has to track what's been eaten.
Oh, I see. So the state has to include Pac-Man's position and the status of every dot.
Every single one. You need a Boolean, a true false, for every pellet. Is this dot eaten, yes or no?
The lecture does the math on this, and
Okay.
it's actually kind of terrifying.
It is. You have your 120 positions for Pac-Man, and let's say there are 30 dots. The total number of states is 120 times 2 to the power of 30.
2 to the 30th. What is that in real numbers?
It's about a billion. So you go from a problem with 120 states to a problem with over 100 billion states just by changing the goal.
That is just wild, and that's only with 30 dots.
Exactly. This is why we can't just brute force it. We have to be smart about how we search.
Okay, so we have this massive universe of possibilities. We need a way to visualize it. The lecture draws a hard line between two ideas: the state space graph and the search tree. I found this a little confusing at first.
Think of the graph as the actual map. It's reality. Arad is a place, it exists once. The graph is the layout of the world.
Okay, and the tree?
The tree is your journey. It represents the what-ifs.
The multiverse of possibilities.
That's a great way to put it, yeah. The start state is the root of the tree. Every branch is a decision you could make. If I go to Sibiu, what happens next?
And the key difference is, in the graph, Arad only exists once, but in the tree,
Arad can appear over and over. You go Arad to Sibiu, then you drive back to Arad. In your search tree, you now have a new Arad node, but this one represents the state being an Arad having come from Sibiu. It tracks the path.
so the tree is recording the history of the plan.
Yes, and that brings up the single biggest danger in uninformed search, the infinite loop.
The Groundhog Day problem?
Exactly. The slides show a simple map where you can go from state S to B and from B right back to S. If your algorithm isn't smart enough, the search tree just grows forever. S to B, B to S to B, on and on.
The tree becomes infinite even though the map itself is tiny.
Correct. So managing this growing tree is the whole game. And the algorithm uses something called a fringe.
The fringe.
Yeah.
Sounds like a sci-fi show.
It's basically the to-do list. The fringe holds all the nodes, all the potential paths that the agent has discovered but hasn't explored yet. It's the border of your known world.
So the whole process is: 1, pick a path from the fringe; 2, check if it's the goal; 3, if not, find its neighbors and add those new, longer paths to the fringe.
That's the loop. But the billion-dollar question is, which path do you pick from the fringe?
Do you pick the newest one you found? The oldest one?
How you answer that question defines your algorithm, and the lecture starts with the most aggressive one, DFS, or depth first search.
The diver.
The diver, yes. DFS uses a last-in, first-out strategy. It always explores the newest path it just added.
So in practice, that means it just keeps pushing forward. It picks a road and just drives. It doesn't look at the other options. It just goes deep until it hits a wall.
And only then does it backtrack to the last choice it made and try the next turn. It explores one branch all the way to the bottom.
Why would you ever do this? It sounds so stubborn.
It is stubborn, but its main advantage is space. Memory.
The slides say its complexity is every Dan or Della.
Yeah, don't worry about the notation. It just means it's really efficient. DFS only needs to remember the single path it's currently on, plus the immediate alternatives at each step. It forgets about everything else.
So it's very lean. It doesn't hog your computer's RAM.
Very lean, but it has two huge problems. First, is it complete?
And complete means it's guaranteed to find a solution if one exists.
Right, and DFS is not complete. Remember our infinite loop. If DFS dives down a path with the loop, it will just spin there forever. It will never go back and check the other branch where the goal might have been waiting.
It gets lost down the rabbit hole.
Totally. And second, is it optimal?
Does it find the best path?
Nope. Not even close. DFS just finds the first path it stumbles upon. The goal could be one step to your right, but if DFS goes left first, it might take a 500-step path all over the map and then say, I found it.
The solution takes 4 days.
But the other solution was 5 minutes. DFS doesn't care, it's done.
Okay, so DFS is the stubborn, memory-friendly diver. What's the alternative? BFS, or breadth-first search?
This is the cautious one, the scanner. It uses a first-in, first-out strategy. It expands the shallowest node first.
The analogy for this is like ripples in a pond, isn't it?
Perfect analogy. You drop a pebble, the ripple explores everything at distance 1, then it expands and explores everything at distance 2. It absolutely refuses to go to depth 4 until it has checked every single spot at depth 3.
So it's very methodical. What does that get us?
It gets us completeness. BFS will never get stuck in a loop because it explores layer by layer. It will find a solution if one is reachable.
And is it optimal?
It is optimal, but only in terms of the number of steps. It is guaranteed to find the solution with the fewest actions.
This sounds amazing. Why don't we just use BFS for everything? Why even bother with DFS?
Because of the cost?
Yeah.
And not time, I mean memory.
The slides had that scary exponential formula.
Black
HMRF.
ace. Bitter dollars to the power of seasons. Think about that ripple in the pond. As the circle gets bigger, the edge, the fringe gets massive. If you have 10 choices at each step, after 10 steps, you have to keep 10 billion paths in your memory.
And you have to hold all 10 billion at once.
Yes, because you haven't explored them yet. BFS will crash your computer long before it finds a solution that's even moderately deep.
So we're stuck between a rock and a hard place. DFS is memory light, but dumb and risky. BFS is smart and safe, but a memory hog.
Welcome to computer science. It's always about trade-offs.
But wait, the lecture introduces a kind of hybrid solution, right? Iterative deepening.
Yes, this is a really, really brilliant hack.
So how does it work?
You basically force DFS to act like BFS.
No.
You run a depth-first search, but you put a limit on it. You say, okay, DFS, run, but do not go deeper than 1 level. It searches everything at depth 1. If it finds nothing, it stops. Then you start completely over. You say, okay, run DFS again, but this time you can go 2 levels deep.
You start over, from scratch.
From scratch.
But that sounds so wasteful. You're just redoing all the work from the first level just to get to the second.
Damn, that's the gut reaction. Why are we recalculating everything? But the math is really counterintuitive. Because the tree grows exponentially, almost all the work is always in the very last layer.
Okay, explain that.
Imagine each node has 10 children. Layer 1 has 1 node. Layer 2 has 10. Layer 3 has 100. Layer 4 has 1,000. The work you have to do to recheck layers 1, 2, and 3 is only about 111 nodes. That's nothing compared to the 1,000 new nodes you're exploring at layer 4.
Oh, so the wasted work is actually just a tiny fraction of the new work you're doing anyway.
Exactly. It's mathematically pretty cheap. So iterative deepening gives you the best of both worlds. It has the low memory usage of DFS, but it finds the optimal path like BFS because it's going layer by layer.
That is really clever.
It's often the preferred method when you have no idea how deep the solution might be.
Okay, there's one last thing we have to clear up. We said BFS finds the shortest path, but we meant fewest steps.
Right. Fewest hops on the map.
But in the real world, not all hops are equal. One road could be 10 miles, another could be 100. BFS treats them as the same. They're both just one step.
Correct. BFS might tell you to take a 3-hop journey that's 1,000 miles long instead of a 5-hop journey that's only 50 miles. It minimizes the action count, not the actual cost.
So BFS is like a flight search that only shows you options with the fewest layovers, even if they cost a fortune.
That's a perfect analogy, yes. It ignores the price tag.
So how do we fix that?
That brings us to the final algorithm in the lecture, Uniform Cost Search, or UCS.
And how does UCS decide what to pick from the fringe?
It stops caring about depth entirely. Instead, it looks at the total cumulative cost of each path so far. It says, okay, path A has cost me 75 miles. Path B has cost me 140 miles.
And it just picks the cheapest one to explore next.
Always. It expands the cheapest path first. It uses a data structure called a priority queue to keep the fringe sorted by cost at all times.
So this is the one that actually finds the shortest route on a real map.
Yes, UCS is guaranteed to find the solution with the lowest total cost. It's the foundation for things like Dijkstra's algorithm, which basically runs the internet and your GPS.
So to recap this whole toolkit, it's like we have different AI personalities. DFS is the diver fast, lean, but gets lost. BFS is the careful scanner safe, but needs tons of memory. Iterative deepening is the clever hybrid. And uniform cost search is the accountant who actually cares about the bottom line.
That's a great summary. And remember, all of this is uninformed. The agent still doesn't have any clue how close it is to the goal. It's just using these strategies to feel its way through the dark.
It's amazing that something as complex as an AI playing chess starts with these simple loops. Check the list, pick a path, expand it.
That's the beauty of it, complexity from very simple rules.
You know, I want to leave you with a final thought. We've been talking about machines, but I can't help but think about how we solve problems.
How so?
When you have a big life decision, a career change, maybe, how do you search for the solution? Are you a DFS thinker? Do you find one option, one job, and just dive deep? You go all in until you hit a wall, and only then do you look at other options.
That's the passionate approach, but you risk getting stuck in a bad situation for a long time.
Or are you a BFS thinker? You have to research every single company, look at every single job posting, and compare them all before you even apply to one, because you're terrified of missing the optimal choice.
That's the analysis paralysis problem.
Yeah.
You run out of mental energy memory before you ever make a move.
Exactly. The computer science seems to suggest the best way is somewhere in the middle. Maybe we should all practice a little more iterative deepening in our lives.
Try something for a bit, see if it works, and if not, take a slightly bigger step next time. I like that.
Thanks for taking this deep dive with us.
My pleasure.
Keep searching. We'll see you next time.